Okay, so you guys are going to tell us about the Truss design project.
Oh, all right. For this physics experiment, we had to design a truss that would hold the most amount of weight. And we learned about compression and tension, and we had to use what we learned to find out how, if you apply a force down, the force is applied, and we had to split the force up into vectors to figure out how much force would be applied at each joint and on the trusses and each component of the truss. And we found out the numbers and how much force was being applied by using trigonometry and splitting up the vectors.
Cool. Okay, so do you guys think you're going to win?
Yes. Possibly.
Possibly. Okay, let's find out. Okay, you ready?
Ready.
Okay, Emily, show us what your group did.
Okay, so basically we tried to use as many equilateral triangles as possible to try to get the weight evenly distributed. And so we were going to have a larger square on the bottom and a smaller square rotated 45 degrees on the top. And we notched these little pieces to hold the corners together, but some of them got notched wrong, and it's a little lopsided, and it should be funny to watch.
Okay, thanks.
Alright, come on.
Before you let me just zoom out and see the stack you're working with.
Okay. Oh my goodness.
Hey, you guys, it's starting to fall towards Megan. So you gotta like hold it. You gotta push it a little bit this way, I think.
I also heard a crack. Oh, there it goes. There it goes. I see the one that's going to go.
There it goes.
Yeah!
All right. Well, the bridge the truss we did. We used the classic triangle designs, reinforced the joints, all that stuff. But really, it's gonna explode, and we're hoping it's gonna explode pretty good, and hopefully it holds a decent amount of books. But we'll see.
I'm looking at the right-hand side, and it's actually still off the ground.
Oh, great.
It still hasn't settled.
It's
going
So,
to the left.
It's definitely going that way. So Zach looks more up over here.
the triangle. Oh.
Someone should hold it.
Oh!
Or not.
Yes! We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 books.
I knew it was going to go that way.
12 books. Come on.
Wait, what are you going to talk
We decided to use a cube so it's flatter on the ground and we can balance things out without it teetering as much.
And for the sides, we used X's with 2 equilateral triangles having 60-degree angles because we did the math for different types of angles and we found out that 60 was the best for the weight distribution. So hopefully it'll be good.
We think our joints on the side are probably going to be first to fail.
Okie doke.
Really, I am.
Wow, I was really expecting this to fail with like one book.
Don't
this was a
guess.
pleasant surprise.
More work, less talk.
Anything.
Wow.
Zach, I have to toss the pile towards you.
Zach, you're a horrible stacker.
Horrible.
I'm trying to get the weight to go like different ways.
Just stack.
Hold on, wait.
Yeah, you.
Don't let it.
Oh! Okay, Laurel, what do you guys got?
Alright, our truss is built very compactly with a lot of supports on the outsides.
And insides.
Well, yeah, but like the sides. And we used larger angles at the bottom and smaller angles at the top because when we did the math out, we noticed that when you change the angle, like even though equilateral triangles distribute the weight evenly, that the smaller you make the top angle, the more drastically it reduces the tension on the bottom, and it doesn't change this as much as it changes the tension.
Excellent. Let's see how it works.
Really bad.
This thing's gonna be sweet.
Laurel, that was some good.
So the thing just literally folded over to the side. Yep. Okay, Kurt, tell us what you got.
Well, hello. This is our truss design, and we modeled it after like an oil derrick. And the way that we did this was we built 4 individual sides and then finally put them together, connecting them to these 2 bases of squares. They have an inward tilted motion, hopefully to distribute the most force by pushing it out down to the bottom and putting these bottom members into tension. this design maximizes all these 4 sides, putting all these members in, hopefully into compression, and then forcing all of it into the base and top to put it out into.
Are you not even touching them?
No, there's no.
That was 200 pounds.
We need the gym weight.
We need more?
Someone sit on it.
Follow me out, people.
How much weight are we at?
Can I just stand on it?
She's twisting.